Hi everyone, please use these solutions wisely. Hopefully you have done the problems and then you can take a look at these and see my explanation for ones that you need help with. Starting with number 6, so we have a transformation that leaves E1 unchanged. So that means that T of E1 is E1. That means that our first vector in our matrix is going to be 1, 0. And then we have, it maps E2 into E2 plus 3 E1. So T of E2 equals E2 plus 3 E1. So what that means is that T of E2 is 3, 1. So the second column of our matrix is going to be 3, 1. Number 7, we have a transformation that rotates points through negative 3 pi over 4 radian and then reflects points through the horizontal x1 axis. Okay, so let's do this visually. So here is E1. E1 is getting rotated negative 3 pi over 4 radian. So that goes to here. Okay. That's after step 1, but then it gets reflected through the x-axis. So that goes to here. So this is T of E1. So our first column of our matrix is going to be negative root 2 over 2 and root 2 over 2. That's actually stated in the hint. Okay, now in blue, let's do E2. Okay, so E2 is here. Let's rotate it by negative 3 pi over 4. That takes us to here. That's after step 1. After step 2, when we reflect over the x-axis, that's right here. So this is T of E2. So our second column of our matrix would be root 2 over 2 and root 2 over 2. Okay, number 8. We've got a transformation that first reflects points through the horizontal x1 axis and then reflects points through the line x2 equals x1. Remember, don't get confused by the notation here. We're reflecting over the x and then we're reflecting over the line y equals x. So what happens to E1? Here's E1. When it gets reflected over the x-axis, it stays there. When it gets reflected through the line y equals x, it turns into this. So this is T of E1, which is the vector 0, 1. So our first vector is 0, 1. Now we look at what happens to E2. This is E2. When it gets reflected through the x-axis, it becomes this vector down here. That's after step 1. When it gets reflected over the line y equals x, it ends up right here. So this is T of E2, which is the vector negative 1, 0. Okay, number 9. We're going to first perform a horizontal shear that transforms E2 into E2 minus 2E1, leaving E1 unchanged, and then reflects points through the line x2 equals negative x1. So that's a reflection over the line y equals negative x, which is this here. Okay, this one might be a little more tricky. So let's follow what happens here. E1 starts here, and it remains unchanged after the shear. So E1 stays. After one step, it's there. After the second step, it's down here. So this is T of E1. That means that our first column of our matrix is 0, negative 1. Right. And okay, E2. Kind of release as they start. So here is E2. It is getting transformed by a horizontal shear to E2 plus negative 2 E1. So that turns into, let's see, what does that turn into? Negative 2 comma 1. So that's going to turn into like right here. So that's the vector negative 2 comma 1. And then when that gets reflected over this line y equals negative x, where will that go? That will go like right here approximately. So that one would be negative 1 comma 2. Okay, so the final vector is negative 1 comma 2. That's where E2 goes. And so that's our second column, negative 1 comma 2. They're done. Okay, number 10. And then on to 13 and 15. Okay, number 10, we've got a transformation that first reflects points through the vertical axis, then rotates pi over 2 radians. All right, this one will be easier. So there's E1. We're going to reflect over the vertical axis to get here. That's after step 1. Oh, okay. And then we're going to rotate pi over 2 radians. Remember, that rotation is counterclockwise. So this here is T of E1. So our first vector in our matrix would be 0, negative 1. Let's look at E2. Here's E2. When it gets reflected over the vertical axis, nothing happens to it. And then when we rotate pi over 2 radians, we fall down to here. And so this is T of E2, which means it lands at negative 1, 0. And so there's our matrix. Moving on to 13. Let the transformation be the linear transformation such that t of e1 and t of e2 are the vectors shown in the figure. Using the figure, sketch the vector t of 2, 1. Okay, now take stock of the notation here. This is really saying t, the function t, is getting applied to the vector 2, 1. Okay, remember what the function t is, how it operates. T is done by matrix multiplication. So A contains t of e1 and t of e2. Remember, we build A by knowing where the unit vectors go, and we're applying the vector 2, 1 to that, which means in effect we're taking 2 copies of t of e1 and 1 copy of t of e2. Okay, so all we have to do is draw that in our sketch. So here is t of e2, and here is t of e1. If we have 2 copies of t of e1, that would take us out to about there. And if we have 1 copy of t of e2, let's try and draw this accurately. We've got 1 copy, something about there. That looks about right. Okay, 15 is next.
Right.
Okay, in exercises 15 and 16, fill in the missing entries of the matrix, assuming that the equation holds for all values of the variable. At first, this looks really challenging. How are we going to find the 9 entries that go in that matrix, which transforms a vector x1, x2, x3 into the given vector? But if we simply decompose the output vector, here's what I mean by that. Let me write the output vector first.
Today I have
Let's write this as a linear combination of 3 vectors.
Oh, no, that's fine.
So let's write this as x1 times 3, 4, 1 plus x2 times 0, 0, negative 1 plus x3 times negative 2, 0, 1. Look what we have. We have a linear combination of 3 vectors, which can be written as a matrix vector product. So the first column of our matrix is the first vector in this linear combination, second column, and the third column. So this is the vector which accomplishes that transformation. Okay, next we're going to 16 through 22.
Which document did I use this one in?
Okay, 16 is very similar to the one that we just did. So we'll write this as a linear combination. I'll do it straight away without all the writing. So 1, negative 2, 1. And the other component would be negative 1, 1, 0. So this means matrix A, which performs that transformation, is 1, negative 2, 1, negative 1, 1, 0. Those are the 2 columns. So A is a 3 by 2. 17. So this is very similar. It's just written in a slightly different form. So we've got a transformation, and we're supposed to just find the matrix that implements that transformation. I'm going to do one of them and then leave the rest to you. So 0, x1 plus x2, x2 plus x3, and x3 plus x4. So if we decompose that output vector, we've got x1 times 0, 1, 0, 0 plus x2 times 0, 1, 1, 0 plus x3 times 0, 0, 1, 1 plus x4 times 0, 0, 0, 1. Okay, so our matrix, which implements this transformation, it takes a vector in R4 and transforms it into a different vector in R4. So we know that our matrix has to be 4 by 4. 0, 1, 0, 0 is our first column, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. Okay, I want you guys to do 16 or 18 through 20 on your own. I'm not going to do those for you. Let's see, 21 is the same, and 22, oh, 20, let's see, 21, no, 21 is actually different. Let's do 21. So I'm skipping 18 and 18 through 20. You do, I'll give you solutions in class. 21. Let the transformation be linear such that t of x1, x2 gives us that. Okay, so here would be our matrix. Our first column would be 1, 4, and our second column would be 1, 5. That's the matrix which performs this transformation. Find x such that t of x equals 3, 8. So this is saying, can we find an input vector which contains x1, x2 such that we get the vector 3, 8? So what vector gets transformed to 3, 8 under this transformation? So let's ref to solve.
So that'll be in my, like I said, I was trying to save the
2 by
last 5 or
3,
so years to
and we've
do
got
as groups
1,
in
1,
class,
3,
but the next couple days we're going to work through
and
the
then 4, 5, 8.
2014 FRTs, so they can start seeing them mixed
Okay,
together.
so we see that the input vector must be 7, negative 4. So this is a 1, 2, sorry, this is an onto and 1-to-1 transformation. The vector is 7, negative 4. We get a unique solution. So we get at most 1 and we get at least 1, which means there's exactly 1. Problem didn't ask for that. I'm just stating that for you. Okay, 22 is similar, but we're going from R2 to R3.
Average was a 3.1.
Okay, so our output vector could be written, well, let's go straight to the matrix. I think you probably get the hang of this by now. We've got 1, negative 1, 3, and negative 2, 3, negative 2. Okay, there's our matrix. We're trying to find a vector x, so that vector is in 2 space, x1, x2, such that we arrive at the vector negative 1, 4, 9 after the transformation. So let's re-ref. We know that this one cannot be both 1-to-1 and onto because it's not a square matrix. So we've got 1, negative 2, negative 1.
Right.
We've got negative 1, 3, 4, and 3, 2, negative, or 9.
Mm-hmm.
Okay, so inconsistent. So see, because this is an augmented matrix, we have a last row of 0, 0, 1. So we know that there is no x. There is no input that produces that output. So no vector x exists such that t of x equals that output vector negative 1, 4, 9.
Right.
Okay. You might laugh that I just thought about asking you if you had any questions, which would be pretty ridiculous. Oh wait, I'm just checking my solution and I made a mistake. Let's see what happened here. We row reduced. Okay, the solution manual is saying there is a solution, so I need to check what I did wrong. 1, negative 2, negative 1. 1, negative 2, negative 1, yep. Negative 1, 3, 4. And I made a mistake in the last row. It should be negative 2. There we go. Okay, so the solution is 5, 3. So scratch this. The solution is the vector 5, 3. Okay, well, from that you learned to 1, be careful how you input the vector, and 2, what happens when there's no solution. That would mean that there's no x. But in this case, you actually do get 5, 3. Okay, last set here, 25, 27, 31, and 32. Okay, 25, 27, what did I say? 31 and 32? 31 and 32.
I've been living on that website, always up.
Okay,
I'm always looking
25. Let's have a look. So the transformation, so it says determine if the specified linear transformation is A, 1-to-1, and B, onto, justify each answer. So it says the transformation in exercise 17, which thankfully I did. All right, so this was the transformation. Why don't I copy and paste it back from where we had up here?
Yeah.
Okay, there we go. Copy and paste. Okay. Let's, we know that in order for this thing to be 1-to-1 and onto, if it's going to be 1-to-1, we need to have no free variables, so a pivot in every column. In order to be onto, we have to have a pivot in every row, or we have to span all of our 4. So let's check this through a ref.
Right.
0, 0, 0, 0. That means something. 1, 1, 0, 0. Okay.
Yeah.
Okay, so we have, we do not have a pivot in every row. We do not have a pivot in every column. So this is not 1-to-1 and not onto. Okay. 27, I'm going to leave to you. Since I didn't do 19, I'm not going to do 27 for you. Check it with rereffing. 31, let's read it. T takes us from Rn to Rm. A is its standard matrix. Complete the following statement to make it true. T is 1-to-1 if and only if A has blank pivot columns. Well, how many columns would be in our matrix? This matrix is an M by N, so we would need there to be N pivot columns in order for it to be 1-to-1. We need a pivot in every column. Okay, and explain why the statement is true. I sort of did. You need a pivot in every column in order, you need to have no free variables in order for this to be 1-to-1. For 32, Similar T-maps Rn onto Rm if and only if A has M pivot columns, or yeah, M pivot columns, because we need a pivot for every row. Okay, that takes us to the end of the assignment. Hopefully that was helpful, and I will see you in class.